Hey, welcome back to Chemistry. This is Miss Gray, and you're watching podcast 6.1. Unit 6 is all about how do we describe the amount of stuff when we're talking about chemical reactions. And so today we're just going to talk about what do we do to measure the amount of a substance. In chemistry, we use what's called the mole. So I want you to consider this question: how long would it take to spend a mole of $1 coins if they were being spent at a rate of 1 billion coins per second? We're going to answer that question a little bit later on once you know what a mole is. So the mole is a way of measuring the amount of stuff. And there's several ways that we could do this. So let's suppose that we have a sandbox, a child's sandbox. We want to be able to measure the amount of sand in the sandbox. What are some ways that you think you might be able to do this? Of course, you could count each grain of sand. This is called counting the particles, right? So you could take the time to lift up each little grain of sand and count it, and set it aside, and then eventually we'd know how much sand is in there. I don't think I want to do that job, though, because that would take a really long time and it would be really frustrating, counting every single little grain of sand. So let's not do that. Let's see. Here's another way. We could weigh the sand, right? We could put it on a scale and see how much it weighs. Then we could measure the amount of stuff, the amount of sand, by its mass, right? Using a balance. Another way is to measure bucketfuls. That would probably be easier, right? How many scoops of sand there are in there. We could use a bucket and measure how many bucketfuls. But the problem is, not everyone has the same size of bucket, right? And so I can measure with my bucket and you can measure with your bucket, but we might not get the same result because our buckets could be different. Like the bucket on a front end loader is way different than a little sandbox bucket, right? Here's how chemists do it. We use moles. Moles allows us to convert the number of particles to mass or to volume, or any of those, to convert between all of those things. And so that's why we use the mole, because it's a very handy unit and it's universal. Everyone in the world is going to use the same amount of stuff to represent the mole. And that's why it's considered an SI unit. For amount of stuff, the SI unit is the mole. And its abbreviation, get this? The abbreviation for mole is MOL. Hey, how about that? I know it doesn't help much, doesn't save you much writing, but that's what we use. And so 1 mole is considered to be this number, 6.02 times 10 to the 23rd particles. So that's how many particles are equal to 1 mole. And of course I have this picture of this furry critter, also called the mole. They're really not related at all. I don't know why they call it moles, but it has nothing to do with fuzzy little critters. It's just kind of a cute guy. So in chemistry, a mole is like a measuring cup. So it's kind of like cooking, only in chemistry we don't lick the spoon. Not a good idea. So let me show you how we use this. If 1 mole is equal to 6.02 times 10 to the 23rd particles, then we've got to define what we mean by particle. Not all particles are the same. You see, elements have particles that are called atoms, and atoms in an element all have to be exactly alike, right? All atoms are the same in an element. Now suppose that we had a compound where there are different kinds of atoms that are chemically bonded together. Then those particles are called molecules because they stick together as a unit. And of course molecules are for covalently bonded substances, right? We just studied covalent and ionic. So moles are our measuring cups. We can use the same measuring cup and then you can follow my recipe. But if we follow the recipe and we don't have the same measuring cup, then that's not going to do us any good. So now let's go back to our Molyneux question. How long would it take to spend a mole of $1 coins if they were being spent at a rate of 1 billion coins per second? I really want you to consider how big this number is. 6.02 times 10 to the 23 particles makes up 1 mole. So first of all, we need to spend the coins, 1,000,000,000 coins per second, right? And each coin is $1. So let's see, how long would that take? First, we're going to take the mole and divide by 1,000,000,000. And then we'll know how many seconds, right? So we would be making 6.02 times 10 to the 14 payments, and that would take 6.02 times 10 to the 14 seconds. All right, well, seconds, I don't know how many seconds that is. It sounds like an awful lot, but let's see how many days that would be. So I'm going to divide by 60 so I can see how many minutes that would take, and I still don't have a number that means much to me. That's a lot of minutes, right? Okay, divide by 60 again, and it's 1.672 times 10 to the 11 hours. Okay, now we're getting somewhere. That's a lot of hours of my life. How many days? Divide by 24, because there's 24 hours in a day, and I'm still at 6.968 times 10 to the 9 days. That's like 7 billion days. Okay, keep going. Divide by 365.25 days in a year. And we get to 1.908 times 10 to the 7 years. That's 19 million years is what it would take to spend 1 mole of coins. This is a really huge number. It's bigger than the national debt by far, for now. You know, depends on who else gets elected next year, right? So it's going to take 19 million years to spend that many coins. A mole is a big, huge number. But remember, atoms and particles like molecules, they're really super tiny. All right, so now let's compare what we mean by moles, right? Grams measure mass. Moles measures amount. And so let's compare these two different compounds, sugar and water. So here's the formula for sugar. It's made up of 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. Whereas this type of particle, water, is made up of 3 total atoms, 2 atoms of hydrogen and only 1 atom of oxygen. So it's much smaller in its particle size. So if I have 1 gram of sugar and I have 1 gram of water, would they occupy the same volume? Would they take up the same amount of space? And our answer is obviously no. They have different densities. So a gram of sugar may take up more space than a gram of water just because the sugar has, you know, more atoms in it and it takes up more space. It would make a bigger pile, right? Okay, how about mass? If I have 1 gram of sugar and 1 gram of water, that's the same exact mass, right? Yeah, because that's what grams are. Now what about moles? 1 gram of each. Does that have the same number of moles? No, because each molecule has a different mass, right? So if I'm weighing out the number of grams, then I'm going to have fewer particles of sugar because each particle itself weighs more than 1 particle of water, 1 molecule of water. All right, how about the same number of molecules? Does 1 gram have the same number of molecules? No, again, we're back to the particle size, right? The sugar is a larger particle size, so they have a different molar mass, and so 1 gram would have a different number of molecules. And of course, for the number of atoms, no way, because sugar has way more atoms for each particle than water does. All right, so now let's look at 1 mole of each thing. If I have 1 mole of sugar, which is 6.02 times 10 to the 23 particles, I have 1 mole of water, 6.03 times 10 to the 6.02 times 10 to the 23 molecules of water. Will they occupy the same amount of space? And I'm going to say probably. The sugar is going to occupy a lot more space because it's just bigger. So if I have more particles that have a bigger size, then it's going to take up more space. What do you think? Yeah, it says, no, molecules have different sizes, obviously. Okay, how about the mass? If I have the same number of particles of each thing, then is the mass going to be the same? The answer is no. The molecules have a different mass. Each molecule has a different mass, and so if I have 6.02 times 10 to the 23 molecules of each type of substance, then the one that has a heavier particle mass for the molecule is going to weigh the most. Now, of course, if I have 1 mole of each, then of course they have the same number of moles. That one's obvious. But what about molecules? If they have the same number of moles, does that mean necessarily that they have the same number of molecules? Yes, exactly. 6.02 times 23 molecules makes up 1 mole. Now how about the number of atoms? How many atoms are in a molecule of sugar? And how many atoms are in a molecule of water? This one should be obvious too. They're not going to have the same number of molecules. Sugar has more. It has 45 compared to only 3 atoms in each molecule of sugar. So that's kind of how moles are related to the amount of stuff. But let me show you what we can do with this now. If I have 1.25 times 10 to the 23 atoms of magnesium, then our question is, how many moles is that? So we're going to start with, oh, I already had this ready. Sorry, I forgot. Forgot that I did that. If I know that 1 mole of magnesium is Avogadro's number of particles, I didn't even tell you. This guy named Avogadro, he is the first one to measure a mole of stuff. So this is what we call Avogadro's number. Wow, that was kind of an important thing you need to know. Then we're going to use this conversion factor in a t-table. So I start with what I'm given, right? Just like any other t-table. Start with the amount that you're given that goes on your starting line. Then we're going to set up our t-table with this at our starting place. So what do we need to do? We've got to put atoms down on the bottom because crisscross cancels, right? How many atoms are in 1 mole? We're going to put Avogadro's number there, 6.02 times 10 to the 23 atoms of magnesium, and then that's equal to 1 mole, so we put 1 mole at the top. So that's how we use this in a conversion factor. We'll put atoms wherever we need to make it all cancel out, right? So now we're going to do the math, because if I cross out atoms here, they're across from each other, I'm left with moles, and that's our target. That's what we were trying to find in the first place. Remember how to do t-tables? Multiply across the top. So it's 1.25 times 10 to the 23rd times 1. You don't need a calculator for that part, I hope. And then we're going to divide by what's on the bottom. So divide by 6.02 times 10 to the 23, and we get 2.08 times 10 to the minus 1 moles of magnesium. Now your calculator might have it written in this way. And that's okay, because it's the same exact number. Just put a box around your answer, because that's the way I like it. So that's how we use moles. Let's do another one. Okay, first question says, what is Avogadro's number? And so, good thing I just told you, Avogadro is the guy that this number is named for, 6.02 times 10 to the 23 particles per mole. We've got to have labels, right? Units, particles per mole. That's Avogadro's number. Next question. How many moles of sodium is 6.482 times 10 to the 23 atoms of sodium? All right, well, let's make a t-table. And we're going to start with atoms, because that's what we're given. We take what we're given and we put that on the starting line of our t-table. Now what's my target? Moles. So I want to end up with moles here. And I'm going to use Avogadro's number as my conversion factor, 6.02 times 10 to the 23 atoms are in 1 mole. Okay, so now it's time for my calculator, and I brought up a calculator here so that you can see what I'm doing. I want you to be able to follow the math. If you don't in the right order, using the right buttons on your calculator, then you're going to get the wrong answer. And some of you have been getting away with this type of mistake for now, but it's not going to work anymore. So we're going to type in 6.48, then use the E button, 23. Notice I didn't push times. This E button is for exponents. This gives us a way to do exponents in the calculator that uses the correct algorithm, using the powers, not using times 10 to the something, because that algorithm is multiplication, not powers. All right, so I'm going to multiply that by 1 and then divide by Avogadro's number, 6.02 times 10 to the 23. So I use the E button to get my times 10 to the 23. And here's my answer, 1.0764. All right, how many sig figs do I get to keep? Looks like I started with 4 sig figs in my problem, and so that's what I want to keep in my answer. So 1, 2, 3, 4. After the 6, I have the number 4, so I don't get to round up. 1.076. So we come back to here. 1.076 moles of sodium. Put a box around your answer because that's the way I like it. The next question asks us to change this many moles of cesium into atoms. So I have 1.03 times 10 to the 5th moles of cesium. So let's put that at our starting place, because that's the number they gave us to start with, right? We're going to change this to atoms. Now this time, mole is on top, so I want mole to be on the bottom. I know that in 1 mole, there are Avogadro's number of atoms. 6.02 times 10 to the 23 atoms of cesium makes up 1 mole of cesium. All right, so now it's time for that calculator again. So I take 1.03, use the E button to get 10 to the 5th, and multiply that by Avogadro's number, 6.02, E23. And then I hit my equals. Okay, that's how many atoms are in 1.03 times 10 to the 5th. That sounds like an awful lot, right? But that's like 10,000 moles of cesium. And each mole has a whole lot of particles. So our answer gets to keep 3 sig figs, 6.02 times 10 to the 28 atoms of cesium. Put a box around your answer because that's the way I like it. Let's do a couple more of these just so you can get the hang of it, all right? Are 8.925 times 10 to the minus 3 moles of sulfur. How many atoms are there? All right, so I've underlined my starting place and I circled my target, so I know how to set up this problem. The thing that I underlined is what I was given to start with, so that's going to go on my starting line of my t-table. 8.925 times 10 to the minus 3 moles of sulfur. And since moles is on top, then I'm going to put it on the bottom in my next step. In 1 mole of sulfur, how many atoms are there? This is where we use Avogadro's number. 6.02 times 10 to the 23 atoms of sulfur are in 1 mole of sulfur. So now it's a math problem, and I'm going to multiply across the top of my t-table, right? This line means multiply. And then I, of course, divide by what's on the bottom. This line means divide, but on the bottom I have only 1 mole, so I don't need to use a calculator to do that division. All right, calculator time. 8.925 E minus 3. How do I get my negative sign? Right there it is, negative 3, times 6.02 E23. All right, so I get 5.37285 times 10 to the 21, and I get to keep 4 sig figs. So 1, 2, 3, 4. After that 2, I've got an 8, so I better round that up. 5.373. .373 times 10 to the 21 atoms of sulfur. And notice this is not very many moles. It's 10 to the minus 3, so that's like millimoles, but it's still a lot of atoms. That's pretty typical. There's a lot of atoms. Atoms are super tiny, right? How many atoms are in 2.12 moles of propane? Propane has the formula C3H8. You know, like the stuff you have in your barbecue grill? So look, they gave me a number to start with, 2.12 moles of propane. And I'm going to use Avogadro's number to convert. So I want 1 mole on the bottom because crisscross cancels, right? I want moles to be across from one another. And in 1 mole of propane, there's of course 6.02 times 10 to the 23 particles of propane. This one's going to be complicated because not all the atoms are the same kind of atoms. So that's how many molecules there are. And in 1 molecule, I'm going to need a new color so you can see on the black. In 1 molecule of propane, how many atoms are there? Let's see, I have 3 carbon atoms and 8 hydrogen atoms for a total of 11 atoms per molecule. So this one had an extra step in it. Boy, it's a good thing we did this together, right? So for every 1 molecule, there's 11 atoms. So now I've gone from moles to molecules and then molecules to atoms. That was my target, was atoms. How many atoms? So now we're going to get the calculator and we're going to do the same thing. Multiply across the top and divide by what's on the bottom. So I take 2.12 times 6.02 E23 times 11 atoms per molecule, and then that's it. I get 1.403864 times 10 to the 25. And of course I can't keep all of those numbers. That's my calculator vomit. So we're going to only keep 3 sig figs, 1.40. Times 10 to the what? Oh gosh, I forget. Times 10 to the 25. And that's atoms of carbon and hydrogen in 2.12 moles of propane. That's it. So an extra step, but a manageable step, right? We just keep going in our t-table using the rule where crisscross cancels until we get to the units that we want. I think we've got one more because we changed things here. Oh no, but our problem has a typing mistake. That's okay. Good thing I'm here, I can take care of it. So we have 1.75 moles of PO4, but that stuff doesn't exist. That's just phosphate. I need barium phosphate in this problem. So let's see, that would be Ba3PO4 2, barium phosphate. So, oh, I just gave away part A. What is the name of this compound? I just did that answer. Oh, well, you all knew that, right? Because you still have your naming card? You better have that naming card. That's going to save your life. So look up PO4 and Ba, and that way you'll know how to name this. Barium phosphate. What is the name? And then B is asking how many atoms are there in 1.75 moles. So let's count up how many atoms are in one molecule. I have 3 bariums, and these parentheses means I have to multiply everything inside there by 2. So I have 2 phosphates and 8 oxygens. So that gives me a total of 13 atoms per unit, right? Per molecule. How many atoms are there? Let's start with 1.75 moles of barium phosphate. And we're going to turn this into atoms. You ready? It's going to take a couple of steps, but we're just going to take small steps and we'll get there. So for every 1 mole, there's Avogadro's number of particles. So 6.02 times 10 to the 23 molecules. Since this is a compound, we can't just go straight to atoms because they're not all the same kind of atom. All right, so now I've got moles taken care of. And I'm at molecules, but that's not my target yet. Atoms is my target, so let's keep going. For every one molecule, there are 13 different atoms. All right, so molecule now gets to cancel away because crisscross cancels. That's why I put molecule on the bottom, right? And I'm going to multiply with my calculator across the top and divide by what's on the bottom. Let's give that a shot. Oh, I got numbers all over the place. Oh well, 1.75 times 6.02 E23 times 13. All right, so I get 1.36955 times 10 to the 25, and I only get to keep 3 sig figs. So if I round this up, 1.36, and then the 9 makes it round up, then I'm going to get 1.37 times 10 to the 25. 1.37 times 10 to the 25 different atoms in 1.75 moles of barium phosphate. There we go. That's a lot of atoms, isn't it? How many moles are in 1.50 times 10 to the 23 molecules of NH3? Haha, I didn't give away the name this time. 1.50 times 10 to the 23, that's a 3, molecules of NH3. And we're going to change this to moles. All right, so let's see. I'm going to have molecules on the bottom because crisscross cancels, and I'm changing molecules to moles. So I always have 1 mole, right? How many molecules is that? Avogadro's number goes here. 6.02 times 10 to the 23. All right, now it's time for a calculator because I already changed molecules to moles. I got where I want it to be, right? Once you get to your target, you can't keep going or you won't be where you want to be anymore. 1.5 E23 divide by 6.02 E23. Okay, 0.249, and that's all the sig figs I get to keep, only 3. 0.249 moles of NH3. So now we have to know the name of this compound. And this is a kind of a tricky question because NH4 is on your naming card, but NH3 is not. NH4 has this name ammonium, but NH3 doesn't. You'll notice there's 2 nonmetals, and so we have to use covalent naming rules. And so we would name nitrogen just as it is, and then use a prefix. Oh, come on, keep up with me, pen. Nitrogen trihydride. That would be a reasonable name for this, but that's not its name. This guy already has a name, and its name is ammonia. Notice how ammonia looks a lot like ammonium because their molecules are closely related and their names are closely related. Ammonia is like the stuff you use to clean your windows and mop your floor. Its chemical formula is NH3, and it's going to come up a lot. So I really need you to know that the name of NH3 is ammonia. If you don't know that, then you're going to struggle for the rest of the year. So get that one memorized, kind of like water. H2O is water, and NH3 is ammonia. Those are the only ones I really need you to memorize. The rest you have on your naming card, okay? So that's how we work with mole. And you're going to need to bring your calculator to class, not an iPod or a cell phone. You need a calculator. So I recommend the TI 30, or what is it, 30? TI 30, I think, is the highest kind of calculator you would need. But you could also bring a graphing calculator or even the Inspire, because I can show you how to use those to get this work done. Anyway, that's it for today, and I'll see you guys later.